Hello everyone, welcome to my channel. In this lecture, we will discuss about the temperature swing adsorption process. With the help of Aspen adsorption, we will separate methane and carbon dioxide mixture with the help of Aspen adsorption by using the temperature swing adsorption process. So first of all, we will open the Aspen adsorption. This is the Aspen adsorption. This is simulation window. This is the process flow sheet window. Here you can see process flow sheet window. So first of all, we will go to component. This is component, and here we will go to configure property. Now we will click on use S1 property system, and from here we will use edit using S1 property. So after clicking on this, we will go to the S1 properties, to the S1 property. From there we will select the component which are methane and carbon dioxide. We will select the property method, like you can use ideal gas equation, Finn-Robinson equation, NRTL, unique as you wish. I am using the Finn-Robinson equation. So this is the S1 property tab. From here we will go to the component and we will add our component. There are two components, one is methane and the second one is carbon dioxide. Methane and carbon dioxide. Now click on next, and here you will see that select the method, property and method. So we will select the Finn-Robinson equation. You can use another equation as you wish. Now go to next. This is the temperature dependent binary parameter for methane and carbon dioxide. Now click on next and click on OK. Now go to the Aspen adsorption and click on OK. Again go to the Aspen property and click on yes. Now go to the Aspen adsorption again and go to the default. Double click on this one and add these two components by clicking on this double arrow. Click on OK, and here now we will make the process flow sheet. So the process flow sheet consists of the feed gas. This is a dynamic model, so this is a feed gas. This is well. So this is well. We will select a well, a feed well, and this is the gas bed, and the this is the product well, and this is the product gas. Okay, feed. So you can rename like b1. This is feed. Right click on it, and this is feed. Click on OK. Now this is b2. Right click on it, click on rename block. This is feed well. Feed well. Click on OK. Now click on b2. Right click and go to rename. So this is bed. Similarly, click on b4, and this is product well. Product well, and b5 is product. Click on it, right click, go to rename block and rename product. Click on OK. So this is feed well, bed. This is the product well. This is the product. Now here go to the connection and gas material connection, because this is a gas stream. So add feed well with bed, connect bed top with top well, and connect product well with product. Okay, this product. Okay, you can now select the whole column and click on control A, control B. So we will align. This is align. Now double click on feed. Double click on feed and add feed specification. Click on feed specification, and the feed consists of 62% methane and 32% carbon dioxide. Here you will see I am adding these from. So the feed consists of 62% methane and 38% carbon dioxide. 38% carbon dioxide. The feed temperature is to 90 Kelvin and pressure is 10 bar. and the feed, this is the feed molar flow rate, 5 multiplied by 10 raised to power minus 6 kilomole per second. Okay, now go to the feed well, double click on it and click on specify. So we have the we will active specification is 3 because we have information about the feed flow rate. So the feed flow rate, here you will see the feed well. Here I have information about this. So the feed, this is the feed well, this is the inlet well, feed well, and this is the product well. So the feed well activity specification is 3, CV value is 100. The C value is obtained from the pressure drop, CV, and flow rate information. So this is the flow rate and this is the feed flow rate. So the feed flow rate is 8 multiplied by 10 raised to 4 minus 7 kilomole per second. So 8 multiplied by 10 raised to 4 minus 7 kilomole per second. Okay, now go to the product well, double click on it, click on specification, and the product well is open. Okay, CV value is 100 and this is, if this is 0 it will be close, if this is 1 that means that value. Now go to product, click on product, click on specification, and suppose the product is favor methane and 0 carbon dioxide. Here we have some information of the product specification and value. So it is favor methane and 0 carbon dioxide. Temperature and pressure are given. So the temperature is 290 Kelvin, 290 Kelvin, and pressure is 9.95 bar. Okay, this is free. The product flow rate is free. Okay, close this one, close this one. Now double click on bed. Okay, double click on bed. The bed is, there is one layer in the bed and the bed is vertical. This is one dimensional and there can be activated carbon or zeolite or some other adsorbent can be used in the bed. So we will click on bed specification, and here this is the material in momentum balance kinetic model isotherms. Which isotherm you are using, the energy balance isothermal or non-isothermal process reaction, there is no reaction, so this is none. Now I have information about the bed. So the bed specification, I have information about the bed specification, mean the what will be the isothermal parameter for methane, carbon dioxide, what will be the radius of the adsorbent. So in this case the adsorbent is the activated carbon, so we will use the information about the adsorbent and the adsorbate. So, which mean the components, we will add the information about component and the bed, the adsorbent, etc. So I will click on this open, click on open and add the information. So I have information about the bed and the component, so I will add these information to save my time. So this is the TSA for methane and carbon dioxide, so I will click on open. Now it will take some time. You can see the simulation window here. It is, this is simulation window, it is taking some time. You can see. Now here you can see this is general. The discretization method to be used is UDS1 and number of nodes is 20. A momentum balance is convection with estimated dispersion, and this is, you can see the momentum balance is the Argon equation. The kinetic model, this is a solid, this is lump resistance, linear, mass transfer coefficient is constant. The isotherm is the extended Langmuir 2. This can be Langmuir 3, extended Langmuir Brenlich, so extended Langmuir 2. And the isotherm depend on partial pressure because these are gases. So for liquid we can use concentration, but here it is gases. Energy balance non-isothermal with gas conduction, and here the heat transfer to the environment is adiabatic. There is no heat transfer to the environment, and the solid phase heat capacity is constant. These values are also constant. Now there is no reaction and procedure. Go to specification. Here you can see the bed height. The height of the adsorbent layer is 0.163 meter, and the internal diameter of the adsorption column is 0.016 meter. Interparticle and intraparticle voidage are also given. The bulk density of the adsorbent is 515.93 kilogram per cubic meter. The adsorbent particle radius and the adsorbent shape vector, it is a spherical particle, so sphericity is 1. The mass transfer coefficient are 5 and 110 for methane, carbon and carbon dioxide respectively. The molecular diffusivity for methane and carbon dioxide are this one in square meter per second. Isothermal parameter for methane, carbon dioxide, all value are given. So here you can see the adsorbent specific heat capacity is this one. This is the solid, the adsorbent specific heat capacity. And here you can see the heat of adsorption, the enthalpy of adsorption. Enthalpy of adsorption for methane is this one, minus 18 megajoule per kilogram per kilomole, and for carbon dioxide it is minus 22 megajoule. Heat transfer coefficient is 1, and here the heat transfer of gas phase, constant of gas phase heat capacity, heat conductivity. So gas conductivity is this one, and the solid conductivity, the adsorbent thermal conductivity is this one in megajoule per meter into Kelvin. And the specific surface area of adsorbent is this one. Suppose the specific surface area of adsorbent is 2057. Here in the we have information about specific surface area. So I will add some information to 2057.14 1.14. Okay, now close this one. Click on initial. So initially there is pure methane in the bed. At the beginning there is pure methane. There is no carbon dioxide. After a certain time the feed will enter and component will absorb inside the adsorption column. So at the beginning there is fresh bed, no carbon dioxide. Okay, now click on initialize, click on yes. Okay, now we will okay, now go to the tool and here go to the cyclic organizer. So and yes, cyclic organizer. Double click our cyclic organizer, and here this is cycle step, etc. So cycle 1. So this is the temperature swing adsorption for methane and carbon dioxide. Methane and carbon dioxide. Okay. Step 1. Description of step 1. Step 1 is adsorption. How much time is for adsorption process? So for adsorption step, suppose there is 60 seconds. I am assuming this value. You can add some other value. It is a time drawing and we are using 60 seconds. You can also give your expression, your variable, etc. by clicking these. Okay, this is step 1. Now for step 1, click on this one and click on right click, or here you can go to the step, go to the manipulated variable. So this is the manipulated, this is manipulated. Click on manipulated and click on variable. So the manipulated, we will add manipulated variable for step number 1. Here we are adding the manipulated variable for the adsorption step. So uh, feed wall active specification, feed well active specification, add this one, click on add variable, feed well flow rate, feed well flow rate, feed well flow rate, feed well pressure, click on variable, feed well temperature. Okay, similarly feed the mole fraction in the feed, methane and carbon dioxide mole fraction in the feed. So we will add methane and carbon dioxide mole fraction in the feed. this one. Methane and carbon dioxide. Methane and carbon dioxide mole fraction in the feed. Sorry, methane and carbon dioxide. Methane and select this one. So it is 0. Now we will delete this one. This is not delete this one. Click on yes. Click on and delete this one. Add variable. So feed one. So feed this one. Methane and carbon dioxide mole fraction. We'll select these two value. Click. So methane and carbon dioxide 0.62 and 0.38. Okay. Now here you can see the first step is in this document. You can see the first step is this is first step is adsorption, second is heating, third is cooling. Okay. These are some information. There is the time, the adsorption time is 60 minutes, but I am using second. I am assuming the time value, not these value. I am assuming timing for these steps. So the first step is adsorption, and the feed well active specification is 3. Feed well flow rate is 8 multiplied by 10 raised to power minus 7. Here you can see 8 multiplied by 10 raised to power minus 7. Okay, the temperature is 290 and pressure is 290. Pressure is okay. Temperature is 298 and pressure is this one. So you can change the temperature like this is 290, so 298, suppose 298 Kelvin. Pressure is 10. Okay. Okay, feed pressure, temperature, composition. Okay, outlet well active specification. So here we will go to variable and here product well active specification. Okay, this one. So here you can see product well active specification is 1. It means it is open. Okay. So this the step 1 is completed. Now go to click on step and click on add insert step. Click on after. Yes, I want to insert my step 2 after step 1. Okay, this is step 2. Now click on this one and click on control. So how much time? So what is the step 2 description? It is here you can see it is step number 2 is heating. And this step we will heat the bed. So heating, and heating, suppose heating is for the heating is it is for suppose it is for 70 second. Okay, this is step 2. And we will add the click on this one and here go to the manipulated. Now we will select manipulated variable for our step number 2. So the manipulated variable for step number 2, which is heating, is this is feed well. This one, the feed well flow rate is 2 multiplied by 10 raised to power minus 7. So the feed well flow rate is 2 multiplied by 10 raised to power minus 7. So I will okay. Okay, the outlet well active specification is 1. Okay, the pressure is 10 and the temperature is 450. 450 is the temperature. Here the temperature is the feed temperature here is 450 because it is heating, so the temperature is increased to 450 in the heating step. 450, it is 10, 1, 3, and in the heating step we are heating the bed with favor methane. So favor methane, there is no carbon dioxide, so methane is 1 and carbon dioxide is 0. Okay, carbon dioxide is 0. Okay, now for step number 3. Step number 3 is cooling. So here you can see cooling is for 60 minutes, but I'm assuming my time, so I'm assuming 60 seconds. not 60 minute. I'm assuming 60 second. You can use 60 minute. The temperature here is only temperature is changing. So for step number 3, okay, this is step number 2. Now I will add. So go to add another step. Do you want to add step after step 2? Yes, I want my step 3 after step 2. Okay. The temperature of the in the heating section is 30. The temperature of the feed stream in the heating step is 300 Kelvin. Okay. And here the pressure and all the variable are same as for step 2. 3, this one, 10, 300, 1 and 0. Okay. And this is step number 3. Now control. 70 second is step 2. Now what is step 3? That is cooling. Cooling. And I want the cooling for 60 second again. For 60 second. If you use 60 minutes, then your simulation will take long time. Your simulation can crash, your window can crash. So I'm using less time uh, in order to converge my problem easily. You can use 60 minutes, 60 hours, depend on your problem. Okay, this. Now go to cycle, and here how many cycle do you want? You can add 30 cycle, 20. I'm adding 10 cycle. Okay, cyclic steady state test. So this is the tolerance of my simulation. This will be the tolerance of the integrated equation. The integrated equation. This will be the tolerance. Okay. Now double click on the create cycle. So that is TSA cycle. The temperature swing adsorption cycle will be created here. Okay, it is activated now. Okay. So this is step 1, 60 second adsorption. Step number 2, heating 70 second. Step number 3, cooling 60 second. Step 1, click on it and check manipulated variable. Step 2, manipulated variable. Step number 3, manipulated variable. Okay. You can change these according to your problem. Now close this one. Go to the flow sheet and once again initialize your problem. Click on yes. Go to initialization and again initialize it. Run is complete. Okay. Click on bed and check whether whether your initialization is okay or not. Click on initial. Click on results. And here bulk concentration in the element CO2 is 00. It is okay. Okay, it is okay. Initialization is complete. Okay. Close this one. Close this one. Now go to the dynamic and click on OK. Click on this one. Here time. So you can see the simulation window. The simulation result here you can see it will take some time for all cycle, for 3 cycle, for the adsorption, heating and cooling cycle. It will take some time. So there are 10 cycles. So this simulation will run for 10 cycle. And for cycle number 1 for adsorption it was 60, then for heating it was 70 second, and for cooling it was 60. So 60 plus 60 plus 70, it is 190, and 190 multiplied by 10, so it will be 1900 something. 1900 here, 1900 is second. Okay, and here you can see this is the convergence. The convergence is this 2 and 3. Okay, and you can see simulation. Now you can plot, for example, if you want breakthrough curve, so breakthrough breakthrough curve. Click on OK and go to the product, go to results, methane, carbon dioxide. Click on zoom full. There you can see this is 500, 1015, and this is. Now you can go to the property, click on X is 1 for each. Okay, here you can see this is step number 1, 2, 3, again one step, 2, 3, etc. Here you can see for carbon dioxide, this is cycle carbon dioxide, and for the green is for methane. Now you can also plot the solid loading, like click on this one, form flow sheet. So solid loading, suppose solid loading. Click on OK. Click on bed. Click on bed. Go to results. Solid loading of methane and carbon dioxide. Solid loading. Okay. Solid loading of methane and carbon dioxide. It's at node number 1 at the beginning. Solid loading of methane at the beginning. Solid loading of carbon dioxide. The solid loading of methane in the middle of the adsorption column. The solid loading of carbon dioxide in the middle of the adsorption column. And the solid loading of methane at the end of the adsorption column, and the solid loading of methane of carbon dioxide at the end of the column. Go to the full and maximize this one. Here you can see this is the solid loading. Go to the property, and here this is the map axis, one for each. Apply this one. You can go to data, grid, line and marker, and no grid, suppose apply. Here you can see this is for methane and carbon dioxide solid loading. Okay. We can also plot the temperature profile, like go to this one, yes, temperature gases, temperature of methane and carbon dioxide inside the bed. Okay, so gas temperature, loading, mole fraction, bulk concentration, gas temperature, gas pressure, gas temperature. At the beginning, what will be the gas temperature? At the center of the adsorption column, what will be the methane and carbon dioxide temperature? At the top of the adsorption column, what will be the temperature of methane and carbon dioxide? Go to full, and here you can see this is at the beginning, the temperature is very large as compared to the temperature in the middle. At the middle, temperature is slightly decreased. At the top, the temperature is further decreased. Now right click, go to the property. You can rename one for each. Okay, go to data, grid, line and marker, and no grid, suppose. Here you can see this is the temperature of the bed. You can also plot another graph, like pressure of the pressure profile, pressure of gases inside the adsorption column. What will be the pressure of methane and carbon dioxide inside the adsorption column? So the pressure, suppose the gas pressure at the top, the pressure of methane and carbon dioxide in the middle of the column, the pressure of methane and carbon dioxide at the beginning of the column. Okay, go to full. Here you can see this is the pressure profile. Okay, you can also plot some other, like I am suppose the velocity, gas velocity profile. Click on OK. Superficial velocity, suppose. Maximum allowable, this is Maximum allowable superficial velocity. Okay, maximum allowable superficial velocity. What will be the superficial velocity of gases at the top, in the middle? That node, this is 10 is mean node. This is 10 is node. 20 is node. This is 1, 2, 3, 7, 8. These are all nodes. These are points in the column. So at point number 1. Okay. So here you can also, this is the for velocity. Okay. Now you can also plot some time graph like profile plot, like mm, temperature, temperature, height, temperature, height. What will be the temperature of gases along the height of the column? So right click, go to the profile variable. So from here you will select the profile variable, click on find variable, click on browse, and click on block. So build, click on OK, click on variable type length or height. So the height of the adsorption column. So the maximum height is 0.163. We have already added this one, this value. So drag and drop. This is height of the column. Okay. Now what will be the temperature of gases? So I'm go to the temperature of gases, like at point number 20, like the temperature of gases. So along the height. So suppose point number 20, point number 20. Okay. Point number 10, temperature of gases. At point number 1, temperature of gases. Okay. Now go to time. So the time 0, this is suppose 100, 200, 500, 1300, 1900. So what at this time, at 1900, what will be the temperature at point number 20? At 1900, what will be the temperature at point number 1? At 1300 second, what will be the temperature of methane and carbon dioxide inside this column, inside this height? This is height. X-axis is height. So again, this is height. Height is on the x-axis. Okay, go to the profile. Here you can see height and click on x-axis. Suppose I am deleting this one. Okay, the height, click on this height, click on x-axis, so it is added. Now 20, click on plot, it is on the y-axis. 10, click on plot, it is on the y-axis. 1, plot, it is on the y-axis. And this is time, 0 second, 20, 100 second, etc. Click on apply, click on OK. Maximize this one. So here you can see this is 0, 100, 200, 500. This is for this. Okay. 0, 100, 200, etc. So these are the time, the time. Okay. So you can see that at 1900, at the maximum temperature is at 1900. The temperature is large. Okay. Now double click on this one and font. Okay. 62, 62. Okay. So here you can see this is the temperature profile along the height. This is the height of the column, and this is the temperature, and this is the time. Now you can go to the property, the map axis, all in one. Here you can see this is the time, 0, 100, etc. Okay. So this was all about that how can we make the temperature swing adsorption process in this one adsorption. Thank you very much.